We are in section 5.4, Troubleshooting Strategies. Observation and equipment history are important in troubleshooting complex circuits. And there's a couple things that can be looked at. First of all, I'll mention logbooks. Logbooks often can provide a history of component failure. It provides the ability to track specific high failure items, and often if there is a history with a given system and it's been well documented, it will be found that there are very specific items that frequently fail. And if a technician has access to this kind of information frequently, he'll be able to go in and rather than spend many hours diagnosing a problem, he can look at, well, this is the high failure items, and just go specifically to those items and see, well, are those the fault at this point? Also, technician experience. Those who have repaired specific systems get a sense of what fails and are able to quickly resolve those faults. And anyone who has worked on a specific system for any length of time, you begin to be able to observe those weaknesses that are in the system, and you begin to develop a knack for quickly identifying the problem, vice a person who has never worked on the system and they have to spend a great deal of time identifying a fault. Troubleshooting fences are used to identify suspected components in a faulty circuit. And this term fence, the idea is that you define boundaries concerning where the fault is located. And there's lots of ways to describe this. Your text uses this term called fences. And the idea on this over here, we see these blue brackets that are showing an entire system. And the idea of fences is that you isolate the problem areas. And in this case, down below here, now we have bracketed in two areas that potentially are the failure items. We've been able to, through testing, we've been able to rule out these other items as being part of the problem, and now we have isolated it down to these items. And that's the idea of using fences. Troubleshooting strategies. Equal probability troubleshooting is a technique that allows you to make a few initial observations and then move troubleshooting fences to include only one or two suspected components. Well, how do you do that? Within the lifetime of a system, certain components tend to fail more often than others, and that's what we had talked about on the previous slide. Using this information, the probability of a failure being a repeat event can lead to faster diagnosis and repair. And as was mentioned on the previous page, logbooks, technician experience will aid in being able to quickly diagnose a problem. Split half troubleshooting. This technique allows you to locate defects with a few measurements. Essentially, the technique involves splitting the circuit path into halves and troubleshooting from the middle of the first half, then the second half, and so on. And the idea is that here, if you have the circuit and there's many potential test points, you measure at the halfway point. If the signal is good at this point, and you have to know what the what is a good signal and what is a bad signal. But if you measure here and you have a good reading, you know the problem is probably over here. If the signal is bad, then you would go back and look at this area, and then again you do more tests. This is essentially what we had talked about, I believe it was in Chapter 1, where we talked about the idea of divide and conquer. Signal tracing and signal injection. And again, these were mentioned in Chapter 1, but we will mention them again here. Signal tracing and signal injection are useful techniques when used with the split half troubleshooting method that was from the previous slide. Instead of tracing or injecting the signal from the beginning point of a circuit, the signal is introduced and traced from midpoints within the circuit. If the output is good, when a good signal is injected at the midpoint, then the second half of the circuit can be ruled out. The fault must be in the first half of the circuit, and the idea here is, in this particular case, we just looked at this one, the idea would be to inject a known good signal at this point, well, the signal that should be here, and then to evaluate, is the signal processed and do we have the correct signal here. If we do not, then we know something is afoul in this area. Component substitution. Once a system has been analyzed and the source of the defect found, the suspected defective component should be substituted to confirm its status. So, you find a component that you suspect is bad, then you replace it. Well, the component that you have replaced, at any rate, needs to be disposed of. You do not want components that either are suspected to be defective or are defective in with components that are known good. Substituted components that do not fix the system should be discarded to prevent their reintroduction into the system. And so installing and uninstalling components can damage them, and this is even in the event that you have components that are good, you install them, then you take them out of the system. Those components should not be reused. Semiconductors are relatively inexpensive, and they can be damaged by putting them into a circuit, taking them out of the circuit, so it's better just to dispose of those and not to put those in with your known good components. In-circuit testing of components, and this is the idea that sometimes you can test components while they're in the circuit. In some cases, the components of the circuit may be tested while still in the circuit. Opens and shorts may be detected with an ohmmeter while the component is still in the circuit. Specialized test equipment is also available for specific component in-circuit testing, and this is a common practice where you actually measure the components in circuits. This is often a tricky thing, though, because when you measure across a specific component, oftentimes that component is in parallel with other components, and so the reading that you would expect with that out of the circuit and when it's in circuit is often very different. So you have to really know what you're doing in order to do this effectively. Okay, so we have this wraps up our look at troubleshooting. We finished off looking at talking about testing components while they're in the circuit. We looked at circuit substitution, briefly looked at signal tracing and injection, split half troubleshooting. This was the divide and conquer from the first chapter. Troubleshooting strategies. And we started here on this page. We talked about the fences and that observation and equipment history are important in troubleshooting complex circuits. We looked at logbooks, technician experience. All of these things will contribute to being a good troubleshooter. Probably one of the major things that makes a person a good troubleshooter is just simply experience, being exposed to a system, working on it, and your troubleshooting skills will grow from that experience.